6.2 Integration by Substitution, Part 1. Your objective for this lesson is to integrate using u-substitution. Okay, so you'll see here that a change of variables can often turn an unfamiliar integral into one that we can evaluate. This is called the substitution method of integration. Basically, your objective for the reason for using substitution is to make your life easier, because some things are just really hard to integrate otherwise. And you'll see here the power rule for integration. This is one that we've looked at before. Basically, when you integrate like x to the third, you're going to add 1 to your exponent, so it'll be x to the fourth, then divide by the new exponent over 4, plus c. This is so long as your n is not equal to -1. If it was equal to -1, then you'd be using ln. So we want to be able to use this rule. Example 1, evaluate the integral x plus 2 to the fifth dx. Now I could try to evaluate this like we've been doing, but it would involve a little bit of guesswork because of this x plus 2. X plus 2 is preventing me from being able to use that power rule easily. So I'm going to take this and I'm going to substitute. I'm going to say u equals x plus 2. Of course, if I'm changing this to u, the dx doesn't really help me anymore. I need to change that to a du. Du here, I know the derivative of 2 is going to be 0. The derivative of x is simply dx. So I can rewrite this integral as the integral of u to the fifth du. So basically, I took what I said u stands for, which is x plus 2, and put a u there. The fifth power was still there, so I added that back in. And since du is equal to dx, I could swap that out 1 for 1. Now I can integrate this using the power rule. So I know that this is going to be u to the sixth, because 5 plus 1 is 6, divided by 6 plus c. My last step here is to actually go back and change the u back to x's. So I have, instead of u to the 6th, I'm going to have x plus 2 to the 6th. And I'm going to have 1/6 of that. If you want to write that over 6, that is fine also, plus c. And this is my answer. Pretty easy. Example 2, evaluate the integral, the square root of 4x minus 1 dx. Okay, so this time I'm going to replace what's under the radical with a u. So u equals 4x minus 1. I'm not going to include the square root here, because if I did that, it wouldn't really be helping anything. I just replaced everything, and I'd still have a little bit of chain rule going on. I'd have an inside function, an outside function. So I'm just going to leave it like this. All right, now we have to find du. And du here is 4 times dx. Now this is a little bit different than last time. I can see that there's a dx here and here. But what about this 4? Well, there isn't a 4 in my original problem. I need to get rid of that. So I'm going to divide both of these sides here by 4. So I end up with 1/4 du is equal to dx. Now I can rewrite my problem. So I now have the integral of the square root of u times 1/4 du. Why? Because this is square root of, I said everything under there is u, and dx is equal to 1/4 du. So I just replaced everything out. Notice I don't have any x's left. I don't want any x's left. I got rid of all of my x's. There should be no more x's. Now I'm going to use some properties of integrals. Remember, if I have a constant inside my integral, I can boot that to the front. So I have 1/4 of the integral, and square root is the same as u to the 1/2 power times du. Now I can evaluate this. So I have 1/4 times, I'm going to raise that up a power, so u to the 3/2, and I'm going to divide that by 3/2, but divide by 3/2 is the same as multiply by 2/3 plus c. Okay, multiplying my fractions, I'm going to multiply them straight across. I'm going to have, well, I can actually cross cancel though first. So that becomes a 1, that becomes a 2. So I have 1/6 u to the 3/2 plus c. But don't leave the u there. U equals 4x minus 1. So put the 4x minus 1 back in there. Now, if you want to write this as, instead of to the 3/2, if you want to say the square root of this cubed, you could do that. If you want to go back and check your work, that would probably be a good idea if you're not really comfortable with this process yet. You could go back and check your work by differentiating. So if you differentiate this function and you end up with what you have here, then that means that you've done your problem correctly. Okay, trig integral formulas, and these should be familiar to you. So if u is any differentiable function of x, then you have these definitions. Remember, they are the same as the formulas for differentiating, but backwards. So, for instance, the integral of cosine u du is sine u plus c. If you were to differentiate sine, you would get cosine. Okay. Example 3. Evaluate the integral cosine of 7x plus 5 dx. Okay. And I could evaluate cosine x very easily here. So you can look here. I have a formula for integrating cosine u, or cosine x. What I can't deal with is this inside piece. So, probably guessed it, we have a u. U equals 7x plus 5. Well, what's du? Du is going to be 7 times dx. Let's rewrite this. Integral of cosine u. Well, oh gosh, I jumped the gun here, didn't I? There's no 7 in this problem. I need to move that 7. So I really have 1/7 du equals dx. So I do have the integral of cosine u, but then I have to multiply by 1/7 du. So the 1/7 du stands for my dx. Now, like before, I'm going to take the 1/7, take it to the front. So I have 1/7 of the integral cosine u du. And we can go back here, and you see my formula for integrating cosine u du is it equals sine u plus c. So I just have 1/7 times sine u plus c. And now I can replace that u with what it's equal to. And we're done. Now, you might be wondering why, and I may have done this on the last problem too, when I have the 1/7 out here, why I don't put that in parentheses and distribute that to the c. You don't have to, basically, because c is a constant. If I have 1/7 c, I could just replace it with another constant. It doesn't really matter what c is, so I don't have to multiply it by that number. Example 4, evaluate the integral 1 divided by cosine squared 2x dx. This one is tricky for a couple of reasons. One is the 2x here, the other is that it's cosine squared, and also that the cosine squared is in the denominator. So the first thing I want to do here, I can very quickly take care of the fact that that's in the denominator, because remember, 1 divided by cosine x is really secant x. So I can replace that, and that's exactly what I'm going to do. So this is really equal to the integral of secant squared 2x dx. And this takes care of another issue too. So if I were to try to integrate cosine squared x, you see that's not really on my list of options. But right here on number 3, I do have secant squared. So that made my life easier twice with one step. So now that I know I could integrate secant x, I just want to take care of that 2x. I'm going to make that my u here. So u equals 2x, which means that du is 2 times dx. Well, I don't have a 2 in my problem, so what will I do? I will divide by 2. I'm trying to make this, I want everything in here to match up to something over here. So 1/2 du equals dx. Okay, so we have the integral of secant squared u times 1/2 du. Taking my 1/2, putting it to the front. 1/2 integral secant squared u du. And what do I have for secant squared u? I have tan u plus c. So 1/2 times tan u plus c. And u, we said, is 2x, so I have 1/2 tan 2x plus c. Example 5, evaluate the integral tan x dx. And again, looking back at our integral formulas, notice that none of them has a tan x here. So we're going to use some trig identities to rewrite this problem. Remember from pre-cal that tan x is equal to sine x over cosine x. So really, this is the integral of sine x over cosine x dx. And each of these can be written as the derivative of the other, although the derivative of cosine x is technically negative sine x. In this case, I want to make my u cosine x. And I'm doing this because the dx and the derivative is on the top of my fraction. If I made sine x my u, then du would be split, and I can't really do that. So u is cosine x, which makes du negative sine x dx. But I don't have a negative in my original problem, so I'm going to have to rewrite negative du is sine x dx. Okay, so I now have the integral of 1 over u times negative du. And I'm going to boot that negative out to the front. It's a negative 1. So I have negative integral 1 over u du. Now I can integrate. And when I integrate 1 over u, it's going to give me ln. Oh, sorry, the du isn't there anymore. So I have negative ln u plus c. Okay, and my u is cosine x, so I need to plug that in. And I have my answer. And that wraps up part 1.